So now we are here, and we're going to walk through using Excel to calculate the four regions of the weak acid strong base problem titration. So essentially we're going to be recreating table 10.2 and figure 10.2. Okay? I've gone ahead and set up kind of our starting place. So we have a weak acid, 50 milliliters, the concentration of 0.02 molar. It has a pKa of 6.27, and so it has a Ka of what? 10 raised to the negative pKa. So there's the Ka. And so the reason, I like to refer to cells, so if we change the pKa to 4, then Ka adjusts, and we want to change the fewest things as possible if we want a different problem. Okay, so we've already figured out the equivalence point is 10 milliliters, although I guess we could do that here. So in milliliters. If you remember, we did that. Let me see where I have it. Yeah, so that's going to equal the volume times concentration of the weak acid divided by the concentration of the base, and that's in milliliters. So there we go. So now we have a reference. Before base is added is our first point, and at this point we have 0 base. Actually, let's look at the titles here. So we're going to look at how much OH minus we added, calculate a new solution volume, and determine the moles of OH minus that we added. From there, we're going to have the moles of H plus unreacted and a concentration. When we get to the buffer part, we'll need to know the ratio of A minus to HA. When we get to the equivalence point, we want the concentration of A minus. And when we get to the excess OH minus, we'll use these last two columns. So we'll move our way across as we go down. And then the final thing we always want is pH. Okay, so the total solution volume is going to equal the initial volume plus the amount added. And let's see if I can do this without making any mistakes this time. I want to put the dollar sign to always refer to 50. Okay, and then moles of OH minus added is going to equal the concentration with dollar sign times the volume that we just added. But that would give us millimoles because we're talking about milliliters. Then divide by 1,000 to give us moles. And obviously it's 0 now, but you know what we're going to do. We're going to drag this down, right? Okay. Now in this initial setup, we just have a weak acid, right? And so we're going to follow the simple equation of x squared over f minus x equals Ka. But if we make our assumptions and our approximations, we remember that K is equal to the square root of Ka times f. Right, and so we're going to make this easy on ourselves, not solve the quadratic, and we're just going to put this as the square root of Ka times f, which is 0.02. And that should actually be, oh, I guess I don't even need this column. That's actually the concentration, isn't it? So let's see. I'm going to delete this column. I'm going to call this concentration. And molarity, right? Because this equation gives us concentration. And that's it for first part, right? We can find the pH from that. So it's going to be negative log 10 of concentration, and I'm going to format this to have 2 decimal places, and we get 3.98. If you look in the textbook on table 10.2, it says 3.99, and that's because we made the approximation instead of solving the quadratic. But it was actually like 3.984 something, so we were actually really close, and I think it's going to be easier to just do it this way, so that's fine. By the way, follow along, please. Make one of these for yourself. Okay, cell styles, I'm going to call it blue. And now we'll move on to the next region where we have a buffer. Right before the equivalence point, I'm going to wrap the text and center. There we go. So let's just start with something like 1/2 mil, and these 2 columns. Oops. Well, if I do this, it's going to carry around down the formatting, but that's fine. We'll go back to normal for now. Okay, so here, right, we have a buffer region. So we don't actually care about concentration of H plus right now. We're going to jump right to the moles of A minus. And the moles of A minus will be equal to the moles of OH minus added, and the moles of H. Whoops. I messed up there. There we go. Moles of HA will be the initial moles minus what we just added. Right, does that make sense? So it's going to be volume times concentration divided by 1,000, right? Because that right there is the initial moles of HA. We could have made that another column, or like a point over here if we wanted to, but that's the initial moles of HA, and then we're going to subtract away the amount that we just added. I want to find the ratio of base over acid, and then from there we're going to use a Henderson-Hasselbalch equation. So pH should be pKa plus log 10 of the ratio. Now, you can simplify this, right? You might notice that columns I and G are the same right now, or that we don't really need column K. You could just simply put here, instead of K3, just put I over J, but it never hurts. It's kind of cool to see how this ratio changes. So now we're going to format this 2 decimal places. We have 4.99. If we look on table 10.2, we had 4.99. And since this region continues, we can add in our volumes that we want and then simply drag down the formulas. So just to make it consistent with the textbook, we'll use these numbers and drag it down, see if it works. Once, shoot, I did it again, didn't I? Yep, forgot it here. $sign on the B3. Did you catch it before I did? Maybe you realized that I made a mistake. And I made another one. Yep. $sign here. Wow. What? Yeah, okay. See, that's the cool thing of doing this in real time. Then you see. There we go. Okay. That looks reasonable. And now I can actually even compare it, and I can see that it's correct to table 10.2. So the reason I like to kind of keep column K around is you can see how this ratio changes here. When we've reached 9.9 milliliters added, we have 100 times, 99 times more base than acid. So that's kind of interesting to see. Okay, this is before, and then I'm going to do at equivalence point. I'll just call it equivalence point. So we have 10, and then everything else filled in, but I actually don't want these to fill in. I just wanted F and G to fill in, because I'm going to do something different now, right? So I will highlight this as another color. And here at the equivalence point, right, I want to find my new F prime, which is A minus. And so it's going to equal the moles of OH minus added. Well, hold on. We'll continue along again here. So the moles of A minus really is just equal to the moles of OH minus added. So then the concentration would be moles divided by milliliters, but that's milliliters, so we need to multiply by 1,000 to get molarity, and there it is. There's the concentration of A, so that's F prime. And if we apply our same approximation, I'm just putting it over here for like a note. It's going to be equal to the square root of, in this case, KB times F prime, and KB equals KW over KA. And if I really wanted to, maybe I should make another column. Oh no, it's right here. Concentration. I already have concentration of OH minus, right? Because X is OH minus, right? So concentration of OH minus is going to be square root of KB, which is KW divided by KA, and then F prime is going to be right here, and there's my concentration of OH minus, and then pH, we've done this before, it's 14 plus log log 10 of OH minus. Or you could have done negative log of KW over OH minus, but this works too. And so we get 9.25, which is now the equivalence pH. And we'll separate this out so we can see it. So there's the equivalence point. Does that make sense? So we did this a little bit differently. I kind of showed the notes over here, right? But we basically not found our new, a concentration of A minus is F prime. And then we apply the approximation. And since that's OH minus, we have to take 14 minus that to get pH. Okay, but we're following along nicely with the book, Table 10.4. So that was essentially the equation for, we have a weak acid first, buffer, and then a weak base. And now we have, after the equivalence point, which is just simply going to be excess OH minus. We'll hit up 10.05 and don't need that. These first E, F, G are always right. But now we're going to be looking at excess. And so it's going to be the amount that we added minus the initial amount of acid. Right? So equal to G minus volume times concentration. Hopefully I won't make the same mistake this time. I'm going to add my dollar signs, but then I need to divide by 1,000 because that product A3 times B3 gives me millimoles. I want moles. So now I have moles of excess OH. Okay. So I think if I were to do this again, I might have another spot here that just shows like moles of initial moles of acid or something, so that we can just refer to that. But that's okay. We can just do A3 times B3 divided by 1,000 because that's what it would have been. Okay, and then once we have moles of excess, then we can divide by the volume to get concentration. Total volume. That's milliliters, so times 1,000 to get molarity. And then I'm going to apply the same.
Daddy?
Just a moment. I can't pause it.
We need your help. What do you wish to come up?
Did Levi press the OK button? I'll be up in a few minutes. I'm almost done. Okay. Okay. I can't. I'll be up there in a few minutes. See if you can figure it out yourself. I can't pause it when I'm recording on the screen. At least I don't think. All I see is a stop button. So kids are watching a show while my wife's putting the baby down for a nap. So they need help, but they can figure it out. Okay. pH. We really are actually almost done here. Because once we have this done, we'll just drag it down for more volumes. 14 plus log 10 of concentration. And we get 9.92. And that's not actually in the textbook. If we do 10.10, yeah, that's in there. Okay. Let's see. Is everything... Am I going to have any errors this time? I don't think so. I think I've done everything correct. We'll find out, I guess. Okay. 10.5, 11, 12, 13. Use the numbers there. And then these three we'll drag down and separate these out, the cell style. And there we go. So do those numbers match up with the textbook? Pretty close. Some of them are a little bit off on the last digit, which might be, let's see, why would that be? I'm not sure. Because we're not making any approximations here in this part. Huh. Well, that's something to figure out. All right, let's plot VB, which is this column, versus pH. Oh, that looks good. So we'll kind of make it look like the textbook. So we'll go from 0 to 16 every 2. Yep. And from 3 to 12. Yep. Looks good. All right, so a couple points. Here's the steepest part is the equivalence volume, right at 10, you can see. And the pH is above 7, because at this point we have a weak base. The flattest part right here is halfway to the equivalence volume, right? So here we have this buffer region, and so it flattens out, and then when we get close to pH, it starts to change, or get close to the equivalence volume, it starts to change a lot, and then now we're just adding base, and it starts to flatten out again at a very high pH. All right, so I think I'll stop this here. The next section is a weak base with a strong acid. So you can try that for yourself and see how it's similar and how it's different. Okay? All right, so I'll get this up as soon as I can. And yeah, keep working on things and let me know if you have any questions.